I think we can start with the seminar. So welcome to today's IRENA online seminar, and it's my pleasure to have Simon Blouin today. I'd like to introduce him to the audience first. So Simon studied in Montreal, and that's also where he finished his PhD in 2019. His PhD thesis was actually awarded the Best PhD Thesis Award in Stellar Physics of the year, so that's super impressive. After that, he moved to Los Alamos, and now he's a CITA National Fellow and Banting Fellow in Canada at the University of Victoria. And there he's working with Falk Herbig. His research interests are white dwarf stars, and today he's telling us about white dwarf crystallization in the Gaia era. With that, the stage is yours.
Thank you. Okay, so well, it's a pleasure to be able to talk to all of you today. So yeah, I will be talking about white dwarfs, and more specifically about white dwarf crystallization. So this liquid to solid phase transition that all white dwarfs undergo at some point in their evolution. So we've learned a lot in the last 3 years or so, in particular thanks to Gaia. And so there were discrepancies that have been identified between our theoretical understanding of white dwarf crystallization and what we saw in the observations. So that's what I will be talking about today. And so, well, just so we're all on the same page, of course, white dwarfs are the final state in the evolution of the vast majority of stars. So basically anything less massive than about 10 solar masses. So it's the stage that you reach once you go through all those hydrogen burning and helium burning phases of stellar evolution, which means that a white dwarf is mostly made of the ashes of helium burning. So for most white dwarfs, you have this carbon-oxygen core that will make up about 99% of the white dwarf's mass. And then around that, there is a layer of helium and hydrogen that was not burned during the previous evolutionary phases. But today, we'll really focus on this dense core, this carbon-oxygen core. So of course, it's a region that we cannot directly observe. So with observation, you're just probing the atmosphere, so the really uppermost layer, but crystallization takes place in this carbon-oxygen core. So this is our focus today. So the conditions there are quite extreme. So we're talking about densities of the order of 10 to the 6 gram per cubic centimeter, and temperatures in the range of millions of kelvins. So of course, one of the main reason why astronomers are interested in white dwarfs is because they can be used as accurate cosmic clocks. So the idea is that white dwarfs simply cool down for the rest of their life because they have no nuclear reactions anymore. So their evolution is simply a question of getting rid of their thermal energy and radiating it away into space. So this makes them useful clocks because by measuring the surface temperature of a white dwarf, which we can do with spectroscopic observations, we can then infer their ages, provided that we have accurate cooling models for white dwarfs so that we know at which rate they actually cool down. So in the details, you also need to measure the white dwarf's mass and its atmospheric composition. But those are all parameters that we can obtain using spectroscopic observations. So measuring stellar ages in general is a very difficult problem. So an example that's often given is that even for our sun, the only reason we know its age is because we have meteorites that we can study in the laboratory on Earth. If you just look at the sun, at a spectrum of the sun, you will end up with very large error bars if you try to determine its age like that. So stellar ages are very hard to get, but white dwarfs are the biggest exception because we have this continuous cooling, which means that the observable properties will change a lot with time. And so that makes them useful cosmic clocks. So this is not a new idea. This has been used for 35 years. So sometimes it's called white dwarf cosmochronology. And it's been used, for example, to measure the age of our galactic disk, the ages of globular clusters, open clusters, all sorts of things. So it's a pretty mature technique, I would say, at this point. But today, with the large-scale surveys to which we have access, there are new applications of this age dating technique that are becoming possible. I've listed here 3 examples, and I won't go in details into them. So just for the sake of time, but one of them is to reconstruct the stellar formation history of stellar populations. So how many stars per year were formed in that population. White dwarfs can even be used to trace back the chemical evolution of our galaxy, as well as the composition of rocky exoplanets. And they may also even be useful in the near future in cosmology. So if any of this piques your interest, please ask me about that at the end, because I could say a lot of things about all those applications. But all that to say that white dwarf age dating really is a technique that has broad implications across many different branches of modern astrophysics. But ultimately, all those applications, they rely on the white dwarf cooling models that we need to infer the ages of white dwarfs based on their surface temperatures. So it's really important to understand the physics of this cooling. So this brings me to the first part of my talk. So white dwarf crystallization as revealed by Gaia. So the image that you see right now is a rendering of the positions of some 300,000 white dwarfs that were discovered thanks to Gaia. So Gaia, of course, is a satellite from the European Space Agency, which is simply just doing only one thing, but it's doing it very well, and it's measuring the positions and distances of billions of stars within our galaxy. So thanks to Gaia, we've increased the number of white dwarfs we know by about a factor 10. So of course that's huge, and that's just over the last 3 years. But even more critical is that for all those white dwarfs, we now have distance measurements. And when you know the distance to a star, well, then you can lift the degeneracy that you have between the radii and the distances of all those stars. And for white dwarfs, if you know the radius, you also know the mass, because white dwarfs obey a very well-known, well-constrained mass-radius relationship. So Gaia gave us access to all this extra information on white dwarfs, which we didn't have before, at least not for that many white dwarfs. And this has really opened the door to testing our cooling models of white dwarfs to see whether they match what the observations tell us. So this figure is a figure I like a lot. So this is the HR diagram zooming just on the white dwarf cooling track. So that's really at the bottom, below the main sequence. So white dwarfs enter the white dwarf cooling track here. So on the upper left, when they're bright and hot. And then as they cool down, they move to the lower right corner, becoming cooler and fainter. So what Gaia revealed is that within this cooling track, there is much more structure than we anticipated. So we can see, for instance, that the main cooling track is divided into 2 branches. So there's a sort of bifurcation here with a gap in the middle. And so those are known as the A and B branches. And it's now well understood that the reason for that is that some white dwarfs are born with more hydrogen than others. So the ones that are born with lots of hydrogen, that have pure hydrogen atmosphere, they form the A branch, and the other ones, they will form the B branch. So those are helium-dominated atmospheres. So if you change the composition, you change the opacity, and you change the colors, so you end up with a different track. But more interesting for us today is the Q branch, which is this fainter feature that we see here. And the Q branch is puzzling at first because it is transverse to the cooling of white dwarf. So white dwarfs cool like that, and the Q branch is really perpendicular to that cooling sequence. So it cannot be an evolutionary track. It has to be something else. And as we'll see, it is actually the signature of the core crystallization of white dwarfs. So before we see why the Q branch is caused by crystallization, let's just talk about what crystallization actually is. So inside a white dwarf, you have this carbon-oxygen core, which is a completely ionized plasma. So this means you have bare carbon atoms, ions, and bare oxygen ions that are interacting together through a Coulomb force. So initially, the white dwarf is very hot, so the ions don't really care about those Coulomb interactions because they have so much thermal kinetic energy to move around. So it would look something like that. But as the white dwarf cools down, those interactions become more and more important compared to the kinetic energy of the ions. And ultimately, they just freeze into a lattice structure, into a BCC lattice structure. And so this is a liquid to solid phase transition. And it's a first order phase transition, which is just a fancy way of saying that this will release latent heat. Now, this release of latent heat is super important for the evolution of the star, because remember that white dwarfs are basically just slowly emptying their thermal reservoir into space. There is no new source of energy, except that this latent heat is suddenly a new source of energy. It's excess energy that the white dwarf has to get rid of in order to continue cooling down. And getting rid of this excess energy will take some time. And this means that this will slow down the cooling of the star. So it's really the same thing as if you put a glass of water in the freezer. If you measure the temperature evolution, you will have some plateau at the crystallization temperature. So this is actually what we see in the Q branch. So those two orange lines that you see here, they delimit the region where we predict that crystallization takes place. So let's say I start with the white dwarf over here. It will be completely liquid. And when it will cool down to that magnitude, then it will start freezing. So as it's freezing, it's releasing latent heat. So it's cooling down more slowly. And that's why we see so many white dwarfs in this region. It's because it's a sort of traffic jam of white dwarfs. They're all cooling down more slowly. So we have this pileup in this region. Eventually, the core is completely frozen when we reach this second orange line. And then the white dwarf will cool down very fast after that, once it's completely solid. So the release of latent heat is an important process for the evolution of the white dwarf. It will delay its cooling by about 1 billion years. But it turns out that this is not enough to explain the formation of the Q branch. So we can look at how many white dwarfs do I have in this Q branch compared to before and after it. And that tells me how much energy has to be released during crystallization, what kind of cooling delay do I have during the freezing process. And latent heat alone is just not enough to explain what we see in the Gaia observations. So another thing that's going on is that what you're freezing is really a mixture of two things. So you're freezing a mixture of carbon and oxygen. And in general, when you have the phase transition of a mixture of different species, the two phases won't have the same composition. So a well-known example of that in chemistry is fractionation. So if you take a liquid mixture of two different species and you boil that mixture, the vapor that you will collect will of course be enriched in the species that's the most volatile. So you have a different composition in the gas versus the liquid phase. But this is not something that's restricted to liquid to gas transitions. In fact, we also have this for liquid to solid phase transitions, which is, of course, the case that's more relevant here for our white dwarfs. So a good example of a fractionation or phase separation process for liquid to solid phase transition is freeze distillation. So this is what, for example, settlers in colonial America in the 1600s, 1700s would do if they wanted hard liquor. So they would take apple cider, which is low in alcohol, and put it in a bucket outside in the winter. And then the next day they come and they remove the ice and just keep the liquid because the water is separated from the alcohol during the freezing process. So we have exactly the same thing going on in our white dwarfs, except that here we're separating carbon from oxygen. So the crystals that are formed in crystallizing white dwarfs, they are enriched in oxygen compared to the liquid phase. And now this will also have a big impact on the cooling of the star. So to see why, well, the first thing you need to know is that the freezing process starts at the very center of the white dwarf. And the reason for that is simply because that's where the pressure is the strongest. So you start freezing at the center, and you form a crystal that is enriched in oxygen. So to form this oxygen-enriched crystal, you had to take some oxygen from higher up in the liquid and bring it down somehow to form that oxygen-rich crystal. And then as the white dwarf cools down, this crystal grows. So you have a crystallization front that's moving outward. And for each new layer that you're adding to this solid crystal, you have to take some oxygen from the liquid phase and bring it into that solid core. And so at the end of the crystallization process, what you've done is that you've transported a large quantity of oxygen from the outer layers of the white dwarf and towards the center. And transporting this oxygen towards the center will release gravitational energy. And this gravitational energy is really similar to our latent heat release that we've just discussed. So it's a new source of energy. It's excess energy that the white dwarf has to get rid of. And again, it takes some time to get rid of this excess energy. And so this also slows down the cooling of the star by about 1 billion years. So a very important effect. Now, if we want to take that into account in our evolutionary models of white dwarfs, a key quantity that we need to know is how much more oxygen is there in my little crystal compared to the liquid phase. So if there is a strong separation, so a strong oxygen enrichment in the crystal, then that would mean, of course, a bigger release of gravitational energy. So the way we measure that is using a phase diagram. So here you have the phase diagram of carbon and oxygen with the temperature on the y-axis and the composition on the x-axis. So you have two lines here. So let's just focus on the red dots for now. So the first line here is called the liquid-zus, and anything that's above the liquid-zus is always liquid. And the other line here is the solid-zus, and everything that's below it is always solid. And now the interesting quantity here is the separation between the liquid-zus and the solid-zus. So this separation tells us how much more oxygen there is in my crystal compared to my liquid. So for example, if I have a white dwarf with 60% oxygen, this is telling me that it would form crystals with something like 75% oxygen. So this is a problem on which I've worked recently with my collaborators at Los Alamos. So we've developed this new technique to really precisely map out this phase diagram. And while it agrees very well with was previously the state of the art, so using molecular dynamics simulation, you can see here in blue. So there's a good agreement overall. We just have a more high resolution picture of this phase diagram now than we had before. But we really think that we are understanding the physics correctly here because we have those completely independent methods that agree very well together. That being said, even if we think we know the physics very well, when we compare our white dwarf models to actual observations from Gaia, we're forced to conclude that there is some big piece of physics that's missing currently in our models. So the upshot is that white dwarfs appear to spend much more time crystallizing than we think they should, according to our theoretical predictions. So there are two problems that have emerged. So the first one is illustrated by the plots on the left here. So on the top panel, you see the observed masses and temperatures of a large sample of Gaia white dwarfs. So you can see most of them are around 0.6 solar mass, and that's just because it's the most common mass for a white dwarf. But more interesting is this pileup that we see here. So that's the equivalent of the Q branch that we've discussed before. So when a star is between those two blue lines, that's when it is in the process of crystallizing. So we see that as those white dwarfs enter this region, they are cooling down more slowly because of crystallization, and we end up with this pileup. But now, if we attempt to replicate this figure, but using population synthesis simulations based on white dwarf models, then we completely miss this feature. So it's as if the white dwarfs evolve too quickly through this crystallization phase. So we don't have a pileup in this region, and we fill out this region of the diagram, which is almost empty in the observations. So from this mismatch, we can infer that there is a missing source of energy in our models that is creating a cooling delay of the order of 1 gigayear. So that's 1 gigayear missing in our models. There's another problem that has been identified for ultramassive white dwarfs. So those are white dwarfs more massive than 1.1 solar mass. So by looking at the kinematic properties of those objects, it's been shown that there's a fraction of them that must undergo an additional cooling delay of 8 gigayears that's currently missing from our models. So I cannot overstate how troubling those discrepancies are for white dwarf age dating, because basically what that means is that all the ages that we have determined in the past for old crystallized white dwarfs, they are underestimated by gigayear timescales. So it's super important to identify what is the missing energy release mechanism that we have to add to our models to better match the observations. And so that brings me to the second part of my talk, which is the solution that I've proposed last year. So to solve this discrepancy, which is the fractionation and distillation of neon-22. So far, I've talked about the core as if it was only made of carbon and oxygen, but of course, there are also some impurities in there. And the most important impurity is neon-22, which makes up a few percent of the white dwarf's core. So neon-22 is interesting because it has 2 excess neutrons in the sense that it has 12 neutrons and 10 protons, whereas the carbon-12 and oxygen-16 that make the rest of the star have equal numbers of neutrons and protons. So the reason why those 2 excess neutrons are interesting is that they can lead to a much bigger release of gravitational energy if there's a way to bring this neon to the center of the star. So to see why this is the case, let's do the following thought experiment. So if we have a white dwarf with 2% neon that's spread uniformly into the star, and let's say now that we have some process that takes this neon and puts it all at the center. So it's not important how we do it, but let's just assume we do that. So during this transition, you have to keep the electron density constant at the center of the star because you haven't changed the mass of the star, which means you haven't changed the pressure at the center of the star because you have to maintain hydrostatic equilibrium. But then the pressure in white dwarf is mostly given by the electron degeneracy pressure. So if you don't change the pressure, that means you don't change the electron density. But now, if you don't change the electron density, that means you had to increase the mass density because neon-22 is giving you fewer electrons per nucleon compared to carbon-12 or oxygen-16. So you have to carry those 2 extra neutrons to the center. And if you increase the mass density at the center, well, that means you have released gravitational energy. And in fact, it's quite simple to do this calculation here to show that for a typical white dwarfs, you have enough gravitational potential energy in your neon-22 to create multi-gigayear cooling delays. So it really looks like the obvious source of energy for those stars is this neon-22. But now the question is, how do you actually take this neon and bring it to the center of the star? So one way to do that that's been discussed quite a lot in the literature in the last 20 years is the gravitational settling of neon-22. So your neon-22 ions in the white dwarf core, because of their extra neutrons, they feel this net downward force. So they will slowly move towards the center of the star, as you can see in this little animation. But as you can infer from this animation, it's not a very efficient process. So the neon-22 concentration at the center has barely changed here. And one of the reasons why this is not a super efficient process is that it's inhibited by the crystallization of the star. So once you form a solid, the neon 22 ions really have a hard time continuing their diffusion towards the center. And so this process is effectively stopped. And so that sets an upper boundary on how much neon 22 you can transport to the center through this settling. So many groups have looked into whether this could be a way to explain the Gaia observation, but really the upshot is that under reasonable modeling assumptions, it just doesn't work. It's not efficient enough to bring this neon to the center. So we've looked at another avenue to transport the neon 22, and that's the phase separation or fractionation of neon 22. So what we did is that we took our phase diagram calculation technique that I've described rapidly earlier for the calculation of the carbon-oxygen phase diagram, and we've applied it to a 3-component mixture, so adding neon to the mix. And the upshot of those calculations is that we find that for typical white dwarf compositions, the crystals that are formed are impoverished in neon compared to the liquid. So you have less neon in the solid than in the liquid phase. And that's very interesting because neon 22 being heavier than your other ions, the crystals often end up being lighter than the liquid in which they form. And so those crystals, instead of just staying where they're formed and letting the crystal, the core grow, the solid core grow, they will want to float up. So this will completely change how the freezing process unfolds. So this is actually a pretty old idea. So it was first suggested in 1990, but at the time they did not have the simulation techniques that we have today to compute those phase diagrams that we need to know the composition of the solid versus the liquid phase. But the idea was already there at the time. So what will happen is that you will have those crystals that are poor in neon and that will start floating up. By floating up, they will have to displace liquid to fill back the gap that's left behind. And this liquid will be more rich in neon 22 because you had to expel neon 22 from the crystal when it was formed. Eventually, this floating crystal will melt. And then this process will just repeat itself again and again. So you float a neon poor crystal, you push more neon to the center, and so gradually you increase the neon concentration at the center of the star. So this goes on for some time until you reach a critical abundance of neon, which is about 20% neon. And then we can predict that the core, the central core will freeze at that composition. So this is really the process we were looking for because it's been able to take all this neon 22 and squeeze it at the center of the star. And in bonus, this is a process that is triggered by crystallization. And a key constraint we have from the Gaia observations is that the missing energy source, it manifests itself during the crystallization process. So this really ticked the boxes to solve this problem. Okay, so another important aspect of this process that I need to mention is that whether you have or not this neon distillation process will depend on the exact composition of the white dwarf. So the important axes here are on the top and on the right. So you have the oxygen mass fraction and the neon mass fraction. So if you're in this blue region, then the crystals are lighter and they float and you have distillation. But if you're in the orange region, they remain heavier than the liquid. So there is no floating. So if we take, for example, a 60% oxygen white dwarf, then this is telling us that you need more than 2% neon to form this neon-rich core. Now, for most white dwarfs, we actually expect less than 2% neon. So for a white dwarf that descends from a solar metallicity progenitor, we expect about 1.4% neon. And so that would place us over here in this diagram where there is no distillation. Except that as the white dwarf will freeze, there will still be this removal of oxygen from the liquid phase because of the oxygen separation process. And so we will start moving to the right here along this orange arrow. And so at some point, we will cross this boundary and we will have the distillation process, except that it will now take place when there is already a central portion of the core that is frozen. So instead of forming a neon-22 rich core, we'll form a neon-22 rich shell, which will also give away a lot of gravitational energy, but much less than forming a neon-22 rich core. So what I've suggested is that those two outcomes that we can predict from those calculations, they can each explain the two cooling anomalies identified by Gaia. So for the ultramassive white dwarfs, the interpretation would be that the fraction of them that have this huge 8 giga-year cooling delay, they would be white dwarfs that have a bit more neon than we expect on average for white dwarfs. And so they would be forming this neon-22 rich core, and this is enough to release enough energy to create 8 giga-year cooling delays. And then for all the other white dwarfs that have less neon, while we predict the formation of the shell, and we've calculated that forming the shell will release enough energy to slow down the cooling by about 1 to 2 giga-years. So that matches, again, very well the observation that we have for the second Gaia anomaly. And another cool thing is that, well, we can predict that this shell will be formed when about 60% of the white dwarf is crystallized. And if you look at this diagram, the pileup here is not at the beginning of the crystallization, it's not at the middle, it's really in the second half. So it matches very well with the expectation that the shell is formed quite late into the freezing process. So we're working now on putting this self-consistently into stellar evolution models so that those effects can be taken into account when measuring white dwarf ages for all those different applications. But there is still one important problem that we will need to solve, and it's an old problem, but it just became even worse with this neon-22 story. And that problem is the problem of how much oxygen there is in my white dwarf when it's formed. So you can see that depending on how much oxygen I have, it will completely change the picture of which of those two scenarios unfold, and that will completely change my predictions for the cooling rate of white dwarfs. And so this brings me to the third part of my talk, which is the work I've been doing over the last year or so, trying to better understand the structure, the composition of white dwarfs. So the way we predict how much oxygen there is in a white dwarf is simply we use 1D stellar evolution models, and we let them go through all the phases of stellar evolution until the white dwarf phase. And then you get some oxygen profile, and we use that for our white dwarf cooling models. But as you go through stellar evolution, there are many important uncertainties. And the most important one right now for this problem is the question of convective boundary mixing. So depending on which prescription you use for the efficiency of mixing by convection, you end up with different predictions for how much oxygen there is in a white dwarf. So this plot here, all the different colors, they're just showing different predictions for different mixing prescriptions. And it's not clear at all which prescription is better, or maybe even, well, probably actually none of them are the correct one. And so this is there's a lot of scatter here in the oxygen abundances. So this induces a lot of uncertainty in our white dwarf models. So what we've started to work on with Falk Herwig at UVic and Paul Woodward in Minnesota is to look more closely at the evolution of a low mass star, so the pre-white dwarf phases, and look with 3D hydro simulation how mixing operates in those stars, so that we can then develop mixing prescriptions that can be used into 1D stellar evolution codes, so that we can then get a clear answer on the composition of white dwarfs. So of course, this is the kind of project that will take many years because there are many different phases of stellar evolution to investigate. So the most important one actually for the white dwarf problem is probably the core helium burning phase. But since we're going to do that anyway, we decided to start with the RGB phase. So on the RGB, you have this shell where you're burning hydrogen, and then you have a radiative region, and around that you have a big convective envelope. So this is what we've looked at, and I will just show and then for the few remaining minutes the key insights we got from those simulations. So before going to the simulations themselves, I just want to say that those stellar hydrodynamic simulations that I'm about to show, they're probably the most realistic you've ever seen. And there are many reasons for that. So the first is that this is done with a code that uses compressible gas dynamics with an explicit scheme. So this means that we are solving the full conservation equation. So we're not doing any sort of inelastic approximations or things like that. The calculations are done in 3D and over the full sphere. Realistic stratification, opacities, extremely high resolution. So the movies I will show, they were done on a Cartesian grid of 2800 cube. So that comes out to a bit more than 20 billion voxels. And another key thing with those simulations is that we were able to do them at the nominal luminosity of the star. So very often in stellar hydrodynamics, you have to boost the luminosity of the stars so that the flow moves fast enough that you can actually do the calculations. But with the RGB, because you reach such high luminosities in the real star, well, we don't need this boosting, so we don't need to then extrapolate our results. So that's kind of very neat. So in just a moment, I will show a movie that looks like this one. So you will see the evolution of the vorticity. So the colors here are showing the vorticity, where red is high vorticity and blue and black is low vorticity. So what you're going to see is just a thin slice like this through the star. So the real simulation is in 3D, but now we're just looking at the thin slice. And so the outer region here is the convective inflow, which in a real RGB star would be just absolutely huge, but we cannot include it all because we want to have some resolution of what's happening inside. So we have to truncate it. It's an important approximation, but it's one we're forced to make. But then inside this convective envelope, there's a radiative zone, and it's in this zone we will see some internal gravity waves that will propagate. So I will go to this movie. So you should now see the movie, but let me know if you don't. So now we're seeing just the convection getting started, and very quickly you see when it hits this convective boundary, you see that it is exciting those internal gravity waves into the radiative cavity inside the star. So the two key questions we wanted to answer with those simulations was, first, do those waves that are traveling there, are they transporting species? Can they cause mixing in the star? Because if they do, that could be a way of connecting the convective envelope with the hydrogen burning shells at the center, and that could obviously affect the evolution of the star. And the second thing we were interested in too is how much mixing there is at this interface here between the convective and radiative zone. And so to answer those two questions, what we did, and I will go back to my slides here, what we did is that we added a dye or a tracer fluid to our simulations, and we placed this dye into concentric shells. So each shell is such that it has a Gaussian radial profile, because that then really makes the calculation of the diffusion coefficient much more easy. And so now I will show a second movie that will be for the same simulation, but instead of looking at the vorticity, we'll be looking at the evolution of this dye. Okay, so initially we see that nothing much is happening, but very quickly you will see that the outer shell here is completely ingested into the convective envelope. And that's super interesting because this shell, we had placed it inside the Schwarzschild boundary of the star. And the Schwarzschild boundary, of course, is where if you do a naive 1D stellar evolution calculation, that's where you assume that convective mixing stops. So the fact that it's ingested into the convective envelopes tells us something about the overshooting of convection. And then if we look at the other rings here, we see that not much is happening. They just stay there. And we were able to use that to measure the diffusion coefficient caused by the internal gravity waves. So we were able to measure some mixing, even though we cannot really see it in this movie. But this mixing seems too weak to really have an effect on the subsequent evolution of the star. Now, if we look more closely at this convective boundary, there are many important, interesting things to see. So this is just a snapshot zooming on the boundary region. So this is the vorticity, as in the first movie, and this is a rendering of the radial velocity. So blue is moving inward and orange is moving outward. And here you can see that there is this big plume that's going and intruding into the radiative zone. And in fact, this white circle here is the Schwarzschild boundary. So we clearly see that the convection does not seem to care a lot about the Schwarzschild boundary, and it just goes much further, so about 0.2 pressure scale height further. So there is this formation of this rather thick convective penetration zone. And what's really cool is that actually it's been known for something like 20 years that from the shape of the RGB in the HR diagram, you can infer that you need to add a 0.25 pressure scale height convective penetration zone to match the shape, the observed shape of the RGB. So it's pretty cool that we can replicate this finding, but from first principles in our hydro simulations. Then another cool thing that you see here is that we see this plume coming into the radiative zone, and we see that this is what's exciting new internal gravity waves. So those diagonal structures that we see on both sides, there are waves that were just excited by this plume intruding into the radiative zone. So the next step is to go one step further in stellar evolution and look at the core helium burning phase to see in particular how much mixing I have at this interface. So during the core helium burning phase, I'm turning helium into carbon and oxygen in this convective zone. So that's like my proto-white dwarf. So you can see how that will be important for our problem. One thing I should briefly mention is that 3D hydrodynamics is not the only way to answer those kinds of questions. So astrosysmology is also now a super useful tool in that domain. So for example, there are now 5 white dwarfs for which the internal composition profile has been mapped using the pulsation periods of those stars. And it's super interesting because what is systematically found is that there is much more oxygen. So something like 85% oxygen in those white dwarfs. And currently there is no 1D stellar evolution code that predicts so much oxygen in white dwarfs. So my dream is that using 3D hydro, we'll be able to develop mixing prescriptions that once we put them into 1D stellar evolution codes, we'll be able to predict composition profiles that look like what is measured with astrosysmology. And if we're able to do that, then we'll be able to confidently say that we have solved this problem. So I will then here with a quick summary. So white dwarf age-dating is a powerful tool that has not yet reached its full potential. There are many new applications that are becoming possible. But if we want to unlock the full potential of white dwarf age-dating, well, we need to get the physics right. So Gaia has challenged us in that respect, but I think that this neon 22 distillation that I've proposed can neatly solve those discrepancies. And now the key uncertainty we need to address is this question of how much carbon versus oxygen there is in a white dwarf. And hopefully with 3D hydrodynamics on one hand and astrosysmology on the other hand, that's a problem on which we can progress in the next couple of years. So thank you very much for your time and attention, and I'll be happy to take your questions.
Thank you very much, Simon, for this wonderful talk. I think we already have some raised hands in the audience. I think Charles has a question.
So thanks for the nice talk. I wanted to ask about oxygen neon versus carbon oxygen.
Yeah.
You seem to assume that ultramassive white dwarfs are carbon oxygen.
That's a very good question. So from a standard stellar evolution point of view, we would expect that white dwarfs more massive than about 1.1 solar mass would have oxygen neon cores and not carbon oxygen cores. But this assumption is being challenged right now because of Gaia. Essentially, what we see is that the Q branch, so where those stars crystallize, really matches with where you expect a carbon-oxygen plasma to freeze and not where an oxygen-neon plasma would freeze. So oxygen-neon would freeze earlier in the evolution. Maybe I can pull back my plot. Give me 1 second. So yeah, so oxygen-neon would freeze, let's say, somewhere around here. Whereas carbon oxygen freezes here. So the fact that we don't see an overdensity in this region, well, the fact that those stars are stopping their evolution here is kind of a strong indication that they actually have carbon oxygen cores. Now, how can you actually form carbon oxygen core for ultramassive white dwarfs? Well, there are many ideas out there. So it could be through mergers. It's not totally clear that if you have a merger of 2.6 solar mass white dwarf, what's the composition you end up with in the end. But there are also things like rotation that can affect whether for very massive stars you can actually burn carbon and form oxygen neon white dwarf. But it is very much an open question. But I would say that we have strong empirical evidence that there are at least some ultramassive white dwarfs that have carbon oxygen cores.
I have a follow-up question to this. I've worked on type 1a supernovae, so thermonuclear explosions of white dwarfs. Yeah. Does the separation of carbon and oxygen affect the ignition of a white dwarf?
Well, this is something interesting. Actually, I've been wanting to talk to type 1a people to see whether this would change anything, because it will change the composition profile. And so I guess probably, and that's something I'd like people to look at, that people who do those mergers. And there are also heavier elements that can be affected. So for example, right now I'm visiting Matt Kaplan at Illinois State University, and we're looking at iron 56, how it could form a dense iron core at the center of the star. And that, I think, is also something that could affect type 1a ignition, so explosion. Yeah. So my answer is, I guess so, but yeah, this should be explored. Yeah,
especially the neon 22 is really important because it has additional neutrons. So when the white dwarf explodes and fuses to nickel 56, so nickel 56 is only produced if you have an equal number of protons and neutrons. If you have additional neutrons, you can form additional nuclei that are not nickel 56. So that's super important.
Cool.
If we have a clock that, or a method that tells us how much of that neon 22 is in the white dwarf, that would be amazing. Do we have any other questions from the audience? I don't see any. So let's thank Simon again.
Thank you.
And as a reminder, we have a discussion session on GatherTown. So anyone who wants to join us and talk about white dwarf crystallization and white dwarfs in general, you're welcome to join Gather. The link is in the email to this to the seminar announcement. So see you in a few minutes.